All right. So, let us look back as to what we did in the last time that we met. We learned about what we call as the physics of setting and mechanism of stretch and bulk generation. Did we do it all complete, or there was something else was left for you to do? Did we ask something to do? No? Did we discuss the role of detwisting? What was the role of detwisting? Can you tell me? Why is the detwisting so important? You see, after setting, you get a twisted filament yarn. This yarn does not have a tendency to untwist. So, what do we get at the end of setting is that you have a multi-filament yarn which has been tested and subjected to some setting operation. So, this yarn does not have any tendency to untwist, but it is not a textured yarn. So, what do we do? So, this was our position where there was an untwisted multifilament yarn. There is another position where you had done some setting. In this case, maybe it was a thermoplastic yarn and you did heat setting, and so the energy kept on coming down and became more stable. So, at the point x 2, it is a multi-filament twisted yarn. So, it is not a textured yarn. So, what do we do? So, we say we do untwisting. When we do untwisting, the energy again goes up because you are doing against the wish of the twisted multifilament yarn. So, energy again goes up. Energy obviously would not like to remain at a higher state, would like to come down. So, if you remove the untwisting forces, what will happen? The yarn would like to go back, and the filaments within the yarn would like to go back to their original position, which they remember as the helical structure. And so, they will go back to the position which they remember. If all of them go back to position x 2, then what do you get? Again a multi-filament twisted yarn, which is again not a textured yarn. So, how do we get the stretch and how do we get the bulk? So, we had only 3 points: twist, set and detwist. So, we have done the detwisting. So, how do you get the texture? How do you get the bulk? How do you get the stretch? Any guess? We have completed the process that was defined and everybody was happy that this is the process. Interesting, isn't it? So, almost every time we thought twist, set, detwist, you are a textured yarn, and theoretically we say there is no textured yarn. So, this is a good situation to understand, and therefore, if exactly the way this goes is what happens, if this is what happens, then of course we have a bad situation. Fortunately for us, it does not happen. Every filament remembers its state of setting, but does not follow the process that its neighboring multifilament or neighboring filament is following. It just goes the way it wants to go spontaneously, wants to go back to its designated position, which is what it remembers. But fortunately for us, all of them take up another position, which is x 3. And why this happens? Because going back to this is the more difficult option actually. Arbitrarily going anywhere is easy. For example, if we tell this class to go out of this room in a single file, it is a difficult option. Everyone has to wait for the other and then follow. And if we do not say anything, then everyone wants to go out in whichever manner they want to go out, and in the end we do not know who has gone out first, who has gone later. If this exactly that happens, then we may not go to the position x 2, and if you do not go to x 2, there will be some other position which is x 3. From the energy point of view, you may actually be at the same level, but the difference will be somewhere else. And what is it? Suppose I have a yarn which was a twisted yarn, and I give some force, fix this up and give some force so that it gets untwisted. Now, for all of the filaments to take exactly the same position as they were before untwisting, then they have to actually follow exactly the same path as the untwisting. For that to happen, you may have to have a situation where not only this is fixed, this is also fixed, and maybe there is another outfit, for example, something like that, which, and the yarn is held here, and you have a mechanism to rotate only the inner part and then leave it, then this might come back. So, you have another fixture which is holding it ideally exactly the rotation, axis of rotation of the yarn remains exactly same, does not change. And so, you twist it by fixing somewhere, then untwist exactly in the same manner, then there is a possibility that you can get this type of a situation where it becomes a multi-filament twisted yarn. So, I said this does not happen. So, what happens? Because there is no control mechanism when they want to go back, and we are happy that there is no control mechanism. So, when a twisted yarn is untwisted, after that you just remove the untwisting force, and then each filament would like to go to its position which it remembers, but does not follow anyone. So, what happens? So, one filament, it takes a position like this, the other filament also wants to go somewhere there. The third filament also goes and remembers whatever it remembers. The fourth filament also, and so on and so forth. All the filaments take up their position what they remember, but they do not want to go back to this shape, because they do not know how to go. Everyone wants to go immediately, simultaneously, without following any other instruction. And so, what you get is a yarn which has more bulk, and so if you stretch, it can stretch also. So, this is the role of untwisting. And if this did not happen, then you will not get textured yarn. Is that clear? So, something which you may like to generally remember, I call them statements. So, it is the detwisting that generates the bulk and stretch, and not twisting. This is twisting. It is the detwisting that generates the bulk and stretch, and not twisting. Twisting is important, but by twisting you are not getting bulk and stretch. You can't say that I will not twist and I will get the same thing, but finally it is the detwisting which is responsible for generating the bulk and the stretch. Is that right? Clear? Textured yarn is a twist free bundle of twist lively filaments. So, there is no twist in the textured yarn. While we started with the multifilament yarn, we did twisting, we did setting, each filament remembered some of the path that were traversed during this twisting process, but there is no twist in the textured yarn, right. But every filament is twist lively, as if the energy is stored in them and they want to release the energy, right. So, all of them would like to go back to a ship, although this word may not be the best to describe, but at some stage somebody who was explaining almost thought that a textured yarn may be assuming some shape where the yarn is twisting over or filament is twisting over itself, and therefore, it is lively. So, you can stretch this whole thing opens and so on and so forth, but now we would rather believe that there is liveliness not because of twist. So, there is a liveliness not because of twist, but because of maybe some structure like this, all right. So, there is a liveliness. So, each filament is lively in the sense you extend, it will go back, but there is no overall twist in the yarn, and that is why you get what we get. So, what have we learned? Now, we have learned, obviously we can say that we have learned the physics of setting, and now we can also say more confidently that we know the mechanism of development of stretch and bulk, right. So, we go further. So, we will be talking now further on thermomechanical texturing, all right. Thermomechanical texturing, that means you are looking at a yarn or a fiber which responds to heat. Mechanical, because you are looking at still twisting, which is a mechanical process, and so we will have that. So, twist texturing. Within that we are looking at twist texturing. Till the time we say that we are talking about something else, we are talking about twist texturing, which means twisting is being used as the mechanism for deformation. And finally, hopefully, if you do this, you will produce a stretch yarn. So, we know there are three methods, but whenever you want to assume anything, think that we are talking about false twist texturing and not talking about Helenka or talking about turbo duo. We are talking about this is more commercially successful and being used, although all of them can be used without any problem. And if you recall again, so it will also involve the same thing called twisting, setting, detwisting and the textured yarn, and that is what we have understood today, that how the textured yarn is produced. General line diagram we just remember. So, the yarn which is a untwisted yarn is fed, it goes over the heater surface and then is guided through to the take up roll and then to the winder where you can wind. This is your line diagram. So, remember there is a primary heater, secondary heater is there, therefore, the name remains primary heater. So, you have a cooling zone, then the heating zone and the twister. The twist above this is 0, I believe, because you have untwisted. Below this zone there is a twist which flows down from this twister all the way to this point. So, you can appreciate hopefully. So, there is this yarn, this portion is a twisted portion, right. This whole is a twisted portion. Beyond this the twist does not flow, above this there is no twist. So, we have all the things as we had discussed before, and this is where we will be working. You can appreciate, we can talk about later, that the level of twist in the yarn starting from the twister, which is this point and going up to this, may not be exactly same. You see, will it be more here or more here? Will it be more at this twister point or at the feed point? Yeah, twister. So, no confusion about it. So, twist level will reduce because there are constraints, friction, everything else is going to come play. And so, if it was only a feed roller and a take up roller and a twist, the situation would have been different. But because you are contacting a heater which also has some friction, there are guides and other guides, and so all of them are going to play some role. And plus, this so called heater is not at room temperature. So, the yarn changes its position also, its softness, its rigidity also changes. So, because of that also there will be some change in the twist level as you move down from twister to the feed roll. So, let us remember whenever we discuss and keep on discussing this texturing till the time we say, well, we are now changing the boundary conditions, we are assuming that we are discussing texturing of fully drawn thermoplastic multifilament yarn, fully drawn, okay, and it is thermoplastic. That is one thing to remember. Other thing is that twisting and thermomechanical texturing is the process that we are using. It is twist texturing, that means twisting, and it is a single heater machine. So, essentially first we are looking at stretch yarns, all right. So, whenever you imagine anything, some statement has been made, you must evaluate the statement under these conditions, right. Not something else can happen, something else can happen, of course, it can all happen. So, fully drawn thermoplastic fibers, because we know thermoplastic fibers, multifilament yarn need not be fully drawn. We are talking about thermomechanical texturing because we can theoretically talk about thermochemical texturing also. we are talking about twist texturing, otherwise we could have said we are talking about turbo duo or edge crimping. No, we are only talking about this, and a single hit machine at the moment, false twist texturing. All right. So, what is the most significant step out of the 3 steps that we have: twisting, setting and untwisting? So, while we said, we made a statement that untwisting is very important, yes, but if you do not do any setting, there is nothing will happen anyway. So, we believe that setting becomes in any thermoplastic systems one of the more important contributors, and all those control systems that you will develop will also be based on the need that the setting would want. And what happens during the setting process? One thing which obviously, and remember when we say setting, it is thermomechanical, we are putting heat. Breaking of intermolecular bonding. So, setting, you said what was happening is that there will be release of energy, and this release of energy will take place either by crystallization processes or by disorientation process. Are you getting the point? So, how will you get to the setting? How will you get to the set? By release of energy, and if you go by the release of energy, then either there will be disorientation or crystallization. Both of them are favorable for us. Is that right? Then the first thing that must happen is breaking of intermolecular bonds. If these bonds are very strong and they do not break under whatever conditions that you set, there will be no change. That means, the molecules within the fiber are going to change their positions. And before that, we were talking about filaments migrating, getting setting and so on and so forth. Now, we are talking about what exactly may be happening. So, one of the things that must happen is there is going to be breaking of intermolecular bonding. What would mean that the molecules that are there will be more free, they will respond to thermal energy, increase their kinetic energy, vibrate and do whatever they want to do. And what will they like to do? They will like to either crystallize or go to a disoriented state. That is called the rearrangement. Rearrangement. So, the molecular chains will rearrange in energetically favorable configuration, and that means either they will go to the crystal formation or disorientation. Both are good for us. So, that is called the energetically favorable configuration, release of energy, release of energy. And then third thing should also happen is stabilization in the new structure. So, you have a new configuration. What is the new configuration? Some molecular chains have done whatever they have done, maybe they have folded over each other and made a crystalline region, or they have just been disoriented, gone anywhere else. Now, you must freeze them. If you do not stabilize the new structure, this can keep changing, then we are not going to be achieving our goals. And so, stabilization, and this is in some sense is done by cooling. So, you do give thermal energy to increase kinetic energy and vibrations within the molecules, which help the breaking of intermolecular forces. Then you allow time, enough time for recrystallization or crystallization or disorientation to happen. It is not a 0 time process, some time is required, that is an optimization. So, some energy for temperature, how much temperature should be given, some time should be given so that these things happen, and then you say before untwisting. Remember the false twist, immediately above the twister, after the twister you have untwisting taking place. So, if this stabilization, that is the cooling, does not take place, then you would have difficulty. And what we mean by cooling is at least the temperature of the yarn, which may be quite high as it exits the heater, at least is brought down below the glass transition temperature, below which we expect much less transitions to take place. Is that right? So, if this is so, then this is the thermomechanical setting. What does it involve? So, there is a rate. Rate means time is involved. So, whenever you talk about rate, there is a time. So, how fast the setting can take place, and when do you think the setting is complete? So, these two things, the completion and rate of setting, would depend on some parameters, all right. One is the polymer itself. Is it nylon? Is it polyester? Is it polypropylene? Their tendency to crystallize at any given temperature is different. Even at their own optimum temperatures also is different. Some of the material, for example, polyester has got aromatic rings in the chain. They are relatively more stable compared to, let us say, a polypropylene, which is aliphatic and immediately has a tendency to go to some position which may be facilitated by nucleation. So, you can crystallize. So, rate of crystallization, extent of crystallization of each polymer is different. So, obviously, it should depend on the what kind of polymer that we use. So, nature of polymer will be quite important. Okay. The molecular weight and distribution. Now, this is an important thing, is unlike other molecules like carbon tetrachloride or water, their molecular weight are fixed, and therefore, their properties are also very, very specific and well defined. In a polymeric system, the molecular weight, of course, it can is a number, but it is very difficult to produce. Even nature cannot guarantee very easily that all the molecules of cellulose in cotton have the same molecular weight. And so, when you polymerize, synthesize, there is no guarantee, only you can have more control, and therefore, you can do a better job. So, what is the molecular weight, you understand, depends on how you measure. So, weight averages, number average, those type of molecular weights you can always do, viscosity average, and so on and so forth. But if we look at the curve, you will always get some curve of this type, unless something wrong is happening. Like if after doing all the things called polymerization, the polymer is in solid state, and then you do something what we call as solid state polymerization, then you might find, well, it may not be such a beautiful curve. It may be bimodal curve. So, some molecular weight of some type or more than the some. So, you may have two averages, as if two types are formed, but let us say normal molecular weight. So, you have the average molecular weight, of course, this will be the one, and then this is the spread. So, this spread is the one which tells you whether the control were good or controls were not so good. You can also have a situation where the average is same and you have a wider distribution. That means, molecules of very large molecular weight as well as molecules of smaller molecular weight are also pretty high. And in a common sense situation also, one can appreciate that the entanglements, after all, everything that is happening in a fiber is due to entanglements of the molecule. Crystallization is there, then the amorphous region is there, the molecules are entangled. If there are short, very short chains versus very long chains, so entanglements of the same chain may be very different, and so the properties, final properties also may not be same. It is also possible that the smaller molecules can change their position much more easily compared to the larger ones. Therefore, this rate and completion of setting would also depend on this property, which you may measure, you may not measure, you may know about it, you may not know about it while you are texturing. Thermal history. That means, if suppose tomorrow we say, well, I have a beautiful filament yarn which has been just obtained after drawing, we said multifilament. Oh no, it also has been stored at a certain temperature for a certain period of time. So, was the temperature 30 degrees, 50 degrees, or you actually heat set it? Fully drawn filament yarn, I have heat set. So, when you heat set, something has changed. All the polymer is same. So, nature of the polymer is same, molecular weight and distribution is same, we using same one, but I have given some additional thermal input also. Then what happens? Then some changes again in the nature of some crystallization, some disorientation may have taken place before you have texturized and before you are doing a further setting. And so, this thermal history will also matter in this completion of setting, no doubt. When a moment you talk about polymer, the moment you talk about rate, so temperature will be an important parameter. Like polyester melts at what temperature? Polyester, that is PET. All right. So, 250 and above, and nylon 6, all right, 215, 220, and polypropylene 160 to 170. All right. So, based on what polymer you are looking at, temperatures will have to change, and that we are not talking about melting temperature, by the way. What will we do? Will you go to a melting temperature, do thermomechanical setting? So, there will be another temperature which will be optimum temperature for setting purposes, where the fiber remains intact, it still looks like a fiber, but internally internal morphology is changing. So, those type of temperatures are the ones which are going to be used. We will talk about it later. And time is important, as we said, that unless the molecules are able to go to the best configuration which they like spontaneously based on thermodynamic conditions, this will not happen. So, time and temperature are going to be very important. Mechanical stress. All those who have studied a bit of structure properties of fibers, you can understand when we talk about a molecule taking a particular shape or a configuration, whether it is folding onto itself to make a crystalline region or it is randomly orienting itself, would depend on at that point what was the stress level in that filament, because all this is also called a relaxation process. Relaxation, molecular relaxation. So, when we said release of energy, it is relaxation. You go to a disoriented state, it is a relaxation. So, if you put additional stress, then the molecule will be constrained by this stress and may not be able to take the best position, because you are putting external stress, but you may have to do it sometimes. For example, of the yarns or of the fabrics, the heat setting sometimes is done in a very relaxed position or in a taut condition, and they believe that if you heat set in a stressed condition, then the orientation of the crystalline regions as well as those of the amorphous regions will be high. You may want it, all right. The molecules may not like it, but you want it. And so, what is the amount of stress that is added? If you remember, if you do the heat setting of the fabrics, when it goes into the center, right, it is not under taut condition. It goes as a relaxed condition, you see the slack also, and as it comes out to the center, then the slack is gone, some changes have taken place. So, now how much slack that you have given will determine the final stress. So, you must appreciate that mechanical stress is going to also affect the rate and of course, then the completion. Medium of setting. And normally, we believe that we are talking about air as a medium, right. It may not be. You are now putting, look at the false twist machine, you are putting your yarn on the surface of a heater, versus you had a choice that the yarn passes through a tube, it does not touch. So, conduction, convection, radiation, they can be also changing the rate at which the temperature of the fiber rises. Okay. Also, theoretically you can think of the medium need not be air, it could be a solvent, because you might find that if you go up to a certain temperature, the filaments gets degraded a bit, it becomes yellow. Says I cannot go to that temperature, but I have to go, otherwise all this relaxation will not happen. So, you say, well, is there any way? Well, as we know that there can be way that you give another medium. So, you might find whatever is happening at temperature T1, it can happen at half T1 if you have solvent or any other kind of assistance that you have. So, medium can change all these things, right. So, we have few minutes. So, let us say before we go for any kind of optimization and so on and so forth, one must know how do we characterize something called a textured yarn. So, there are two parameters, one is called crimp rigidity and the other is called crimp stability. I mean, when we characterize a textured yarn, of course, we may be interested in tensile properties also, breaking stress, breaking elongation, modulus, we may be interested. But if you remember the stretch yarn, so the curve is like this, and what does it mean? It means that the final tenacity at break may not be so important, because it can stretch 350% before it takes up the real stress. So, why something gets stressed is because I bend, so some stress is here, but if all the fibers and filaments just extend without actually at such a low stress level, then why will it go to the break? Anything breaks because you have actually gone to the breaking point, right. And so, you might find that while we be measuring, and there may be reason why we measure, but the properties that you should be concerned about are the properties which define the textured yarn, which is the crimp rigidity and crimp stability. So, let us say if we have time enough to see at least one of them. So, crimp rigidity is defined as that if you have this yarn, you stretch fully, so you have, let us say, we call this fully extended length as L1, and then you allow it to relax, it goes back and contracts the length as L2. Then this is how you define it. That is L1, if you put a load of this much, okay, that means this relaxation that is happening also has a certain load, let us say 0.002 grams per denier. You see very small stress, right. What it means is that you, how do you measure? So, this standardization is that full extension is not an issue. If you have a load of just 0.1 grams per denier, all the crimps are gone, and theoretically you may have extended up to 300%, all right. But so you have two loads, one is called the light load and the other is called a heavy load. So, initially you put both the loads, let us say it also has some hook. So, you have a light load, another hook, and you have a heavy load. This is how you hang. So, initially you hang the total load, which is the summation of the two loads, and then remove the heavy load and allow it to contract. Of course, for a certain time you can't do infinitely, say let us say I go it for 1 minute, and then you measure the L2 and then describe this. This will be called the crimp rigidity, all right. Although one could have said one should call it as a crimp recovery, but the term has stayed, it is called rigidity, because some rigidity within the so called helical structure is responsible for it to attain this shape, right. Therefore, this term rigidity has stuck to us in the textured thing, and this was called a Hetra method. Hetra was is like Hosiery and Allied Textile Research Associations. So, this was in England. So, they generated this method, and this method is what it is used. So, we should stop here because you may have something else to do today, and next time when we meet we will pick from here and go further. All right.